Welcome to the seminar series on sewer and pipeline engineering. My name is Bert Bosseler. I am the Scientific Director of the IKT, Institute for Underground Infrastructure. In this seminar we will deal with the so-called trenchless construction methods. That means the laying of sewers and pipes without digging trenches. As an introduction, I would like to give you an overview of the fields of application and of the various methods. And I would like to divide my presentation into three sections. First of all, we will look at the task and reason for pipe laying without trenches. Then we will look at some typical applications. And finally, we will take a closer look at the technology and the typical methods. Let's start with a reason for use. Well, if you are following this seminar, you are probably already familiar with this picture. A small view into the underground of our cities. Supply lines and cables are typically located in the pavement area and not too deep. Larger sewers are usually in the middle of the street and in greater depths. At the top we find the street, and soon it becomes clear digging a trench here does not only disturb the traffic on the street, but also the residents. However, it is also clear that there is not much space underground, and it is certainly not easy to use drilling or boring machines in this crowded underground. However, trenchless construction is extremely attractive. Pictures like these from the Society for Trenchless Technology clearly show why it is worthwhile to lay pipes without digging trenches. In general, the aim is to avoid disturbing the surface and to keep the surroundings intact. This concerns road traffic, the road surface, and adjacent buildings, vegetation, or other underground pipelines. In general, many problems and points of criticism for the open construction method are considered advantages for trenchless construction. In these advertising images, we again see examples of damage to plants and buildings, and also the annoyance of residents, for example through noise and dirt. So now in the following section we will take a closer look at typical applications. When does it make technical sense to build without trenches? Here we see a first example in the center of Prague. You can see the old pavement and the buildings have a very special charm. Large trenches would destroy this, and the access to buildings and shops would also be more difficult. Nevertheless, construction is going on here. On the left we see a blue drilling machine in action. With this machine, a pipeline is led from a so-called starting pit to a far-away target pit. Except for these two pits, the surface remains completely undisturbed. On the picture on the right, we see a second typical application. In front of us there is a river, and the new pipeline should lead under the river to the other side. Very similar to the city center example, a rig is drilled under the river in such a way that the pipeline can finally be pulled in. So we can see that if we do not want to disturb the surface, or if there is an obstacle on the surface, we typically build using trenchless methods. But this is not the only reason. Purely economic considerations can also lead to the use of trenchless methods. A typical case is the laying of a sewer at great depth. Here we see an example. We look vertically into a starting pit, and this is 45 meters deep. Down there the pipes are pressed forwards, one after the other, by the use of so-called jacking presses. At the front, at the beginning of the pipe string, the soil is removed by a machine and conveyed out. Of course, a trench could also be dug 45 meters deep, but the costs for excavation, shoring and drainage would be gigantic. However, in pipe jacking, that's how the method is called, only the starting pit and the target pit are excavated. At this depth of 45 meters, this too can quickly account for half the total construction costs, but then the total sum may still be okay. So now we have already seen some technologies and methods. But how can we classify and distinguish them in principle? Let me first illustrate this with two quite extreme examples. This first example is a method that is very easy to use, especially for small pipelines and short distances. It is the so-called soil displacement hammer or impact mole. The special feature is that the hammer works its way through the ground completely independently. To do so, inside the device a weight is accelerated forward with compressed air. The weight hits the drill head, which breaks up stones, for example. Then the remaining energy is transferred into the device itself so that the whole hammer is pushed forward. The moving weight then slides back again and the whole thing starts all over again, so it goes tock, 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 tock forward. In detail, there are of course differences in the machine technology, but that is the basic principle. Three things are particularly important for us here. Number one, the soil at the front of the hammer is displaced to the sides. That means the soil is compacted in the area around the pipe. Number two, the hammers are used without special steering or control. It is non-steerable. We see the principle at the top of the picture. The machine operator places the machine in the starting pit in such a way that it will run towards the intended target. In this case, this is the red-white bar on the right. But the actual construction process remains uncontrolled. If the hammer is deflected in the ground, it will arrive at the target with some deviation. For short distances, the deviation is then not too big and you can accept that. Well, and then number three, the diameter is very small in this case. So nobody can run into the pipe and, for example, take care of the machine in front. We therefore speak of an unmanned process. All in all, we can say, and that is what it says in the headline of the slide, the method is unmanned, non-steerable, soil displacement. Let us now look at the other extreme. Methods with soil removed, steerable and manned. A typical example is the pipe jacking process in this picture. In pipe jacking, the pipes are lowered in a launch pit and pushed forward with the main jacking station. The first step is to install a pipe jacking machine, which we see here in the front. With a cutting tool at the so-called shield, the soil can be removed. It is then transported through the pipe string into the starting pit. The soil is conveyed, for example, with a flushing liquid through a transport pipe to a separation plant above ground. The actual pipe installation then functions in such a way that the pipes are installed one after the other from behind and pushed forward. Since the pipes are pushed through the ground, there are of course frictional forces. The jacking station then must overcome the resistance at the shield and also the friction between the pipes and the ground. In order to reduce the frictional forces, the diameter of the jacking machine is usually larger than the outside diameter of the following pipes. This creates an annular space between the pipes and the ground, and this can be filled with bentonite so that the pipe is lubricated and friction is reduced. At some point, however, when many pipes have been installed, the necessary forces become too great. The last pipe would be subjected to all the forces and would be overstressed. In this case, we can install intermediate jacking stations in the pipeline. With these stations, the pipeline is then driven in stages. First, the front pipe string is pushed forward, then the rear one, then the front one again, and so on. Finally, the presses are removed from the intermediate jacking station and the pipes are pushed together. The jacking machine itself can usually be controlled directly at the front or at a control and steering station in the starting pit or above ground. The direction for the movement of the shield machine is then determined by the position of the shield. In the shield itself, there are so-called steering presses which help to position the shield. The shield can then be used to steer back to the target line again and again, even if the ground conditions change and deviations occur. All in all, therefore, this procedure applies to our three criteria. Number one, the soil is removed. Number two, the whole thing is steerable. And number three, the procedure is manned. So we can work directly on the tunneling machine with personnel, for example to remove obstacles or to repair the machine. With these two examples, we have seen now how the methods for trenchless construction basically work and how they can be differentiated. However, we were also able to see that even for trenchless construction we need openings to the ground, at least an entry and exit shaft, also called launch and reception pit. A distinction is then made between unmanned and manned methods, non-steerable and steerable methods, and in methods with soil displacement or soil removal. Our two example methods are then easy to classify. On one side we have the soil displacement hammer or impact mole. It is unmanned. In our example, non-steerable, and the hammer is used to displace the soil to the side. On the other hand, we have the pipe jacking. It can be manned, it can be steered, and the soil is removed. Of course, these are not all methods we know and use for trenchless construction. There are many other methods which also form a combination of the criteria shown. Some typical methods are listed here. We will go into this in more detail in a moment. It is interesting to see which selection criteria play a role in practice. When do we use an unmanned method, when a steerable one, and when do we use soil displacement? We can see the most important selection criteria here. First of all, there is the length to be driven and the accuracy in line and level. The longer the line is, the sooner we need a steerable construction method. Otherwise, a small deviation at the beginning will turn into a large target deviation at the end. Especially important for the choice of the method are the ground conditions and possible groundwater. Groundwater must be supported in front of the machine to prevent it from penetrating the pipe string. And a dynamic displacement is again difficult in groundwater, as the water cannot be displaced abruptly in soils with poor permeability. In some soils, steering is also difficult because there is no resistance to change direction. The parameters on the right-hand side play a particularly important role in soil displacement methods. The diameter of the pipe determines the amount of soil to be displaced into the surroundings. Adjacent structures must not be damaged, and we need a minimum cover so that the surrounding soil can be compacted and no damage can occur at the surface. But let us look at further methods for construction in more detail. Here are a few more interesting examples. For example, the soil displacement hammer or impact mole. It is also available as a steerable version, as we see in the picture below. Here the hammer sends a signal to the surface, which can be followed there. If the deviation from the target path is too great, then the hammer can be readjusted. The drill head is specially shaped for this purpose. It has an asymmetrical orientation so that it would normally drift to one side during the process. However, on straight sections, the drill head rotates constantly so that it should remain in a straight line. If there are any deviations from the target route, then the rotation of the drill head is stopped and the drill head drifts in such a way that it is realigned to the target route. Here we see a horizontal ram with which an open pipe is driven into the ground. The earth core entering the pipe is generally pushed out hydraulically or flushed out or drilled out mechanically once the ramming process is completed. When designing the steel pipes, the dynamic loads must be given special consideration. Pipes with a cement mortar lining cannot be installed using ramming method. The mortar would simply flake off. Also, in highly swelling plastic soils, the application is difficult. In hard rocks, it is not possible at all. Groundwater is a fundamental problem for all dynamic processes. If necessary, groundwater lowering is required here. Here we see an example of the auger boring process. A steel pipe string is driven into the ground with the help of a jacking and boring unit. At the same time, the soil at the front is extracted by means of a drill head. The soil material is removed in the same process with a screw conveyor lying in the pipe. Here we see a picture from the starting pit. The presses are supported at the rear by an abutment wall. Let's move on to microtunneling. This method is similar to pipe jacking but for smaller diameters. Changes of direction are carried out by the steering head within the shield. The head and the cutting tools must be adapted to the ground and groundwater conditions. Another characteristic feature is the type of material transport, by using a fluid or a conveyor belt. If necessary, the excavated soil is crushed to a conveyable grain size. Here we see microtunneling with auger spoil removal. The drill head and the screw conveyor are driven from the starting pit by use of an auger boring machine. In this example, we use a fluid conveyor to transport the soil. The excavated soil is conveyed hydraulically and separated from the medium by means of a separation plant. The type and quality of the pumped medium, as for example bentonite, must be adapted to the ground and groundwater conditions. In this picture we see a combination of an earth pressure balance shield and slurry pumping. The extracted soil is transported out of the shield chamber by a screw conveyor and further transported by a slurry pump. The soil slurry in the shield chamber is removed just slowly enough to ensure that there is sufficient counter pressure at the working phase. Well, we continue with the pilot jacking method. First, the pilot pipe string is driven along the target route. The steering process is supported, for example, by surveying with a theodolite, an electronic camera or a laser. Changes of direction can then be initiated by turning the slanted tip of the pilot pipe. Subsequently, the product pipe with the same or larger outer diameter can be driven forward, while simultaneously pressing or pulling out the pilot pipe. Larger outside diameters then require soil displacement or soil removal in one or more cycles. Here we see another example of a pilot pipe jacking. Here, the pilot pipe is already installed by using soil removal. Another trenchless method for pipeline construction is the horizontal directional drilling method. Here, a drilling rig is used at the surface to lay a pipe in a shallow underground arch. The drilling rig drills a pilot hole by means of water jetting, which is filled with a drilling liquid, for example bentonite, to stabilize the borehole and to bring the extracted material to the surface. A so-called bag reamer is used to enlarge the hole to the final size of the pipeline. Finally, the product pipe is pulled through the hole. Directional drilling often requires a large pre-drilling area so that the pipe can be aligned before it is pulled into the borehole. Another classical method of underground construction is the gallery excavation. It is used especially for the renewal of sewers and is based on techniques already known from the mining industry. Here we see an early example from Nuremberg in Germany. The description on the right was found in the documentation. Let me read out a translation into English. The tunnel was secured with steel support arches and timber shoring. Driving was done by hand. The excavated sand was carried away with wheelbarrows. The sewer was then concreted in the protection of the shoring. Well, here the steel arches shown in the picture are so rigid that the loads can be borne with little deformation. In this picture we see another more recent example. Here the steel arches are much slimmer. The arches deform under load to such an extent that horizontal bedding reactions are activated. The whole thing therefore behaves like a flexible pipe soil system. A new pipe can then be laid in the protection of the lining. Here, for example, a concrete pipe with an egg-shaped profile. The annular space between pipe and shoring must then be carefully filled with grout. This is the only way to ensure that no excessive subsidence occurs if the shoring decays later. On this picture we see some interesting buildings and sites in the city of Cologne in Germany. In front of us lies the river Rhine. Over the Rhine runs a bridge with the express train line to Frankfurt. Right next to the river runs a federal road. And I took the photo myself above from the roof of the famous Cologne Cathedral. But that is not the most important thing for us as sewer engineers here. We are more interested in a construction project that runs directly under the main road, next to the railway. Here, a large stormwater sewer is being built underground using gallery excavation. On the surface, you only see the yellow side container and an access pit. The rest happens unnoticed underground. Here we see the tunnel's face. The worker mines the soil by hand. Directly at the river, the soil is very sandy and it is easy to mine by hand. Then a steel reinforcement is set and the whole thing is lined with shotcrete, as you can see in this picture. Later, under the protection of this lining, the new stormwater outlet was concreted out. Of course, the larger the cross-sections become, the closer we come to tunnel construction, with its very special methods. Here I would like to give you just one example. In this picture we see the erector of a tunnel boring machine. It is used to join the tunnel segments into a circular ring, directly behind the shield. This has two major advantages. On the one hand, the segments are smaller than the pipe cross-section and therefore easier to transport. Secondly, the pipe is created directly behind the tunnel boring machine, so no frictional forces between pipe and ground have to be overcome. Here we see a large interceptor which was already built in 1975 in Hamburg using a tunnel lining with reinforced concrete segments. Finally, I would also like to mention the pipe materials. Here we see an overview of typical materials used in sewer construction. We can say that almost all of these materials can actually be used with some type of trenchless construction method. With pressing or jacking methods, for example, pressure-resistant building materials such as concrete or reinforced concrete can be used. Plastics, on the other hand, can be pulled in quite well. And even clinker and natural stone could be used in gallery excavation. And that brings me to the end of this seminar session. We've learned that it is worthwhile to build trenchless, especially when the sewers are deep and when there are obstacles on the surface or when we want to avoid disruptions on the surface. Furthermore, we have seen many different technologies and methods to choose from. There are manned and unmanned methods, steerable and non-steerable methods, and the soil can be displaced or it can be removed. And if the cross-sections are very large, then we can also fall back on classical methods of tunnel construction. Thank you.